Yeah, and yeah, thank you. And thanks, Tashpal, for his wonderful overview. And okay, and then the second part, I will present you the technical details about how to maintain in this length constraint expand hierarchies efficiently. And here's today's outline. So, like, we'll start from two tools called local cut match and dynamic routers. And then we use these two tools to develop an efficient algorithm um, to maintain the length constraint expanded decomposition. And with this, we can construct our dynamic vertex classifiers. And combining these two ingredients like expanded decomposition and classifier, then we can build a length constraint expanded hierarchy as Dashpal said. But before building the hierarchy, we also need to take care of the recurse issue that arises in the dynamic vertex classifiers algorithm. Okay. And at the very beginning, I want to make some remarks. Like in this talk, I will assume that all the graphs are constant degree and directed graphs just to make the statement cleaner and easier. And also if this graph have at length, that length will be integral and it will be polynomial bounded. And there are three important parameters that appears everywhere in this talk. Like the first one is the trade-off parameter epsilon, which controls the trade-off between the approximation and the update time of the final distance oracle. And you should always think this of a tiny constant. And then the second parameter is the length parameter h, and I will set it to be n to the epsilon. So basically it means like in this talk, I will only take care of like bounded distance up to n to the epsilon. Yeah, and if you listen to Andy's talk yesterday, like using the technique of stacking emulators, you can like generalize everything to make it work for general distance, like up to poly n. And the third parameter is the congestions or expansion parameter phi, and I will set it to be 1 over n to epsilon squared. Okay, and the final thing is the notations. I will use O epsilon 1 to denote constant factors. And O hat notations will hide factors, some small polynomial factors at most n to the epsilon cube. So basically it means I will not hide h factors or 1 over 5 factors inside these O hat notations. Okay, good. And let's recap some definition about moving cut. Like in a graph, an h length moving cut is just a function that assigns each cut value, which is a multiple of 1 over h, like 0, 1 over h, 2 over h, and blah, 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 or 1. And the size of this cut is the summation of total cut value over all the edges. And the graph G minus C is the graph after applying this cut on G, which is basically the same graph, but with different edge length. And basically, each edge will receive length increase like h times c. Yeah, and actually, maybe in this talk, I will sometimes use like length increase, like use the integral length increase to refers to this fractional moving cut. Like in the integral length increase corresponding to c is just like scaling up c by a factor of h. Yeah, just to make everything integral, then it will be more comfortable. Yeah. Okay, and now we are ready to talk about the first two, like local cut match. Okay, what is a cut match? So given source vertices and sink vertices A and B, the cut match consists of a matching M and a moving cut C. The matching M will match partially the source and the sink. Like as you can see in this figure, it matched two subsets AM and BM. And each can be embedded into the original graph G with like embedding path is h length, and also the embedding should have congestions 1 over 5. Like this green path are the embedding of the matching. And about the moving cuts, after you apply this moving cut on the graph, and this will separate the unmatched part, like the rest of the A and B, like AU and BU in this figure, to make them H far. H far means like vertices in AU is like have distance larger than h, like to vertices in BU. Yeah, and this cut should have small size, only a 5 fraction of the number of source vertices. Okay, and then how to compute this? Like I will just briefly, like based on use this approximate length constraint max flow algorithm as a black box. Okay, just ignore what I wrote here. Like just look at the last 2 lines. Basically, it just output the same thing. Like it output a partial matching between A and B. Is H length, but with congestion 1. And it also output the cuts. This cut will separate A and B, like to make them H far. But the only drawback is that this subroutine didn't guarantee that this cut C have small size. And it's kind of easy to handle this. Like we just need to iteratively apply this subroutine on the unmatched part of A and B. Like in one iteration, if we find a very large flow, like has value larger than 5 times A, then it means that we get a fairly large matching that can match a 5 fraction of source and sinks. Then we are good, and then just go to the next iteration. And otherwise, like the flow value is small means, okay, the cut value is small. Like, okay, so the size of the cut is only a 5 fraction of A, and we are also okay with this, and just terminate the algorithm. And this figure is just an example, like we have 3 iterations, and the first 2 iterations give us 2 matchings M1 and M2, and the last iteration give us a cut that separated the rest of the A and B. Yeah, and to see that the final matching, like the union of M1 and M2 have congestions like 1/5, just because like the number of iteration is 1/5. Because every iteration we make good progress, match a 5 fraction of things. Okay, but actually, this is not enough. Like if we only get a linear algorithm, like almost linear algorithm for computing cut match, it's not enough for our application. What we want is, we want to compute this cut match in local time. Local means the running time only depends on the number of the source vertices. Like A times some small factors. And I'm not going to explain how to do this. It basically we basically localize the approximate length constraint max flow algorithm. Yeah, but I want to emphasize that to obtain this localized version of cut match, we need some additional requirements. Like for example, in this talk, we assume that the graph is constant degree. Then this subroutine requires that the sink vertices is the complement of the source vertices. Like so that now the figures become like here, like each vertex is either a source or a sink. Yeah.
How do you do this length constraint max flow? Is it related to big cost flow?
Length constraints max flow is actually, yeah, it's based on the previous work by Alice and Tetravon. Yeah, and Bernard. And basically, yeah, it has some, like, because actually we allowed this length constraint subroutine will have a poly edge factors in the running time. So it's like, it's fairly not like, because of this poly edge factor, it's not that hard to, like, there give up some space to do this, like to implement this subroutine.
But here we're doing it only for the distance of generation. And we're going to do okay. So then, very roughly speaking, would you just take the graph and make like a deck of that edge, right? You copy every edge, like H, it's not a deck, it's a H. It kind of goes here, and yes, maybe over approximate like H factor. Down, repeat H times. Like generally, H is small. it's not completely trivial, right? And there's lots of stuff to do, but in some sense, it's very different from having arbitrary max flows or inverse max flows. The hardness really comes from flow passes being arbitrary. To pull the H makes it easier, just multiplicative weight stacks and tiny passes.
Okay, yeah, thanks for nice explanation. Yeah. Okay, then like we just conclude a bit on this converge part. Like, yeah, if you didn't follow this algorithm, that's fine. You just remember that we have some algorithm that match something and cut something with a small cut. Okay, and the next two is dynamic router. Like we first recap the definition of router. Like a unit length graph R is a H gamma router. If every vertex unit man can be routed in like H steps and congestion gamma. Here, vertex unit, I mean each vertex can send or receive 1 unit. Yeah, and our goal is to maintain H gamma router R with max degree D. Here, the factor H should be a real constant. And factor, like the parameter H should be a real constant. And gamma and D can be something like close to constant, like n to the epsilon to the 100. Yeah, and because like we control the max degree of this router, so this router is actually a very sparse graph. Yeah, and we need to handle it under like constant batch of updates. Like the first type of update is edge deletions, where we like remove some edges from the routers and require the algorithm to output some set of prune vertices, so that after removing the prune vertices, there's no failed edges. And again, like the prune vertices should not be too many. It should be just like roughly linear to the number of edge failures we receive. And this gap between the size of P and the size of FR is, I will call it the recurse of this dynamic router. And we are aiming at recurse close to constant. Yeah, and the next operation we need to support is like matching insertion, which we received a matching that will match some new vertices we knew to the old router. Actually, there's nothing to do here, but just union the matching to the router. And we just need to show that after this union, the router is still have good quality. Yeah, and here's the initialization of the router. That's just as what Sachapon said. So I will skip here. Like we first pick a constant degree, constant expander, and then take the power graph of this expanded W. Yeah, and like because the K power graph just means like we add a shortcut between vertices with distance at most K. So the step of the routing in R will drop by a factor K. So it dropped from log n to log n over K, which is like constant when epsilon is constant. Yeah, and the max degree is like close to constant because like K is not too large. So it's like the exponential of K is like close to constant. Like because the original normal expander have constant degree. Okay, so basically we have a good router at the beginning. And how to maintain this? Like again, like we give a backblock reduction to the expander pruning. Like just quickly recap what expander pruning do is like it receives a normal expander, which has expansion phi and some edge deletions. Then it can output a set of prune vertices so that after you removing these vertices, the expander is still 5/6. Like it's still a 5/6 expander. And the size of this prune vertices is not too large, only like grow up by a factor of 1/5W. So we just like generate the corresponding edge deletion FW, like given the edge failures on the router. Like so, as you can see in this graph, like you just take the router, take the W edges that is incident to the endpoint of failed router edges, like the dashed edges. Yeah, and then we just apply expanded pruning on this on this edge failures FW. And we can do this because like this expanded W is has constant degree, and it means that the size of the FW, like the number of edge deletion in the underlying normal expander, only blow up by constant factors compared to the size of the edge deletions to the router. Okay, then the step 3 is normal. We just prune this vertex out from W and also R. Yeah, and like it's very easy to see that this invariant holds like R is always a super graph of the kth power graph of W, because we just like remove vertices. So like the steps parameter H is unchanged. And what we lost, like we lost at the expansion of the underlying expanded W, lost the constant factors, and this will cause some blow up on the conjections of our router, and it will cause. Yeah, but each batch of update, this will only blow up by constant factors. So if you finally want to handle constant batch of updates, it is still fine. Okay, and the next thing is like matching insertions. Like there's nothing to do in the algorithm, just take the union. And to see that like the parameters change like this, we just consider how to route the vertex unit demand in this new router. Like we consider a demand pair in this demand. If this demand pair is between old vertices, like the black vertices, then we can just route it as a usual because we didn't remove anything from the router. But if the demand pair is between new vertices, like in this figure, suppose it's like between two green vertices U and V, then we can just first route the items of U and V through these matching edges, and then ask the corresponding black vertices to finish the remaining routing. So basically, the step will increase by 2 additively because we now route along 2 more matching edges. And the congestions blow up by a factor of 2 because now each black vertex will take care of 2 units of demand. One is from its original demand, and the other one is possibly from the green vertex matched with. Okay, and here's the figures, just like how these dynamic routers will look like when there will be constant batch of updates. Like it basically includes a core. This core basically is the power graph of the underlying normal expander. And there will be some affiliated trees like appended to each core vertex. And these green trees are generated by the matching insertion. Yeah, so actually when we do pruning, when we handle edge deletions, we first apply the edge deletions on the core, and then when we compute a prune set of the core, like the P core here, we just include the affiliated trees of these prune core vertices and output and let the real prune vertices to be all of them. Okay. Yeah, and this is the part of dynamic routers. And with these 2 subroutine, local cut match and dynamic routers, we can finally see how we design the efficient dynamic length constraint expanded decomposition algorithm. Yeah, and again, we recap the definition of HS length by expanded decompositions. So HS length by expanded decomposition is roughly, it is just an H length moving cut C, such that after you're applying this cut C on the original graph, like G minus C now becomes a length constraint expander. So for better understanding, we look at the flow characterization of this G minus C. It means any vertex unit H length demand in G minus C can be routed over HS length paths in G minus C with congestions roughly 1/5. So we want to route H length demand, then we obtain like H length path, HS length path. So basically there will be some length like S here. And our goal is to maintain this H length cut C in a certificate. And it should have the following property. First, the size of the cut should always be roughly at most 5 factors of the graph size. This is just like what the static expanded decomposition algorithm guarantee. But the certificate will certify that any vertex unit H length demand in G minus C can be routed over HS length paths in the original graph G with congestions 1/5. Okay, here the length slack should be a real constant so that we can achieve constant approximation finally. And another important thing is here we somehow relax the definition by allowing the demand to be routed on the original graph, not G minus C. So in other words, it means that actually we didn't maintain a length constraint expanded decomposition, but maintaining a weaker version of this. But this is not a big problem, at least for our applications and perhaps other applications, because like we are indeed allowed to route on the original graphs. Like this cut C is something we added artificially. Okay, and before we move on, let's recap the formal definition of what's the certificate of expanded decomposition. So it includes a cut with small size and a pairwise cover of the graph G minus C. Okay, pairwise cover is just something similar to neighborhood cover, but have some weaker guarantee. Like, yeah, I'm not going to explain it here. Like, okay, basically, it just guaranteed that it didn't guarantee that each neighborhood will be covered by a cluster, but we only guarantee that each pair of close vertices will be covered by a cluster. And then we associate for each cluster S in the pairwise cover, we just correspond it to a router R. So basically, like the router should have the same vertex set as the cluster. And another important thing is, okay, this router is the instance of our dynamic router, so that we can maintain this kind of thing efficiently. And the last thing is an embedding that can simultaneously embed all the routers into the original graph G with length like H embed and congestions gamma embed. Yeah, just to compare with the witness expanded decomposition that appears like in the previous talk in this workshop, like we use a weaker object pairwise cover instead of neighborhood cover. And the router we use our instance of dynamic router. And also we allow that the embedding is on the original graph G instead of G minus C. Yeah, and this is a quickly recap why this is indeed a certificate of the expansion of this expander. So basically it's certifying the following. And the reason it's certifying that H length demand in G minus C can be routed over roughly H embed length paths with congestions gamma embed. Yeah, to see this, we first consider an arbitrary H length demand and then allocate the demand pair to the cluster. Like, because this is H length demand, so we can always find a cluster that containing both endpoints of this demand pair. Okay, and then we route the demand pairs on the router, and this only takes like a constant length slack, and this will cause like close to constant congestions. And then we unfold this router paths using the embedding, like we substitute each router path with the underlying embedding path on the original graph. And this will cause will cause some multiplicative factor on both the length and congestion, that is H embed and gamma embed. Yeah, and just for simplicity, we say that this CNR pi is an H5 certified expanded decomposition if the parameter H embed and gamma embed is very good. Like H embed is roughly H, and gamma embed is roughly 1/5. And now we can restate our code as, okay, given H and phi, maintain an H5 certified ED. Yeah, I'm not going to talk too much about the initialization because it is just some similar things to the witness expanded decomposition. So we can use the algorithm that Alice mentioned yesterday. The only thing we need to take care is that we need to embed our dynamic router into this witness expanded decompositions. And this require that our dynamic router should be sparse and the pairwise cover should have small width. Yeah, and then we are now ready to talk about how to maintain this kind of certified ED under edge insertion and deletions. But before that, let's clarify what's the thing we care about. Like, of course, we care about how these parameters, like the quality parameters, like H embed and gamma embed, will then become worse and worse. And also we care the correctness of the algorithm, but the most important thing is that we care the recourse of this certified ED during the maintenance. So to be precise, we care the recourse of the cut C and the recourse of the pairwise cover N. Yeah, because this, as we will see, this kind of thing will propagate to the dynamic router, to the dynamic vertex specifiers. Yeah, and now let's give a formal definition of the recourse of the cut. Like we will see that the cut will change incrementally. So initially we will have a cut that have size 5 fraction of the graph. And then each update, we will add some new cut into our cut. And the size of the new cut should be roughly linear to the size of the batch update. So in other words, the cut has recourse defined as the ratio between the size of the new cut and the size of the batch updates. And then it means that the cut has recourse close to constant. Yeah, and the small point here is a little bit counterintuitive, is why we allow this size of the new cut to be roughly linear to the batch of the update. Yeah, why it's not just in the initialization case, there should be a 5 factors, the size of the new cut should be only a 5 fraction of the batch update. Well, the answer is, okay, why not we allow the size of the new cut to be roughly linear to the size of the batch update? Someone will ask, well, we need to guarantee that the total cut size should always be at most a 5 fraction of the graph G. But this is not a hard thing to handle, even with this guarantee, because when we are when the batch update become too large, larger than 5 times the size of G, we can just restart the whole algorithm to guarantee that the size of the cut is always a 5 fraction of the size of the graph. So basically, what I want to point out is that the size of the cut is has nothing to do with the speed how this cut is changing. And we allow this recourse to be close to constant just because we can handle it later on. Yeah, and let's move forward to define the recurse of the neighborhood cover or of the pairwise cover. So basically, the pairwise cover will change fully dynamically, and the vertex will move in and move out. And the recurse of it basically is defined as the ratio of the times of vertex move in, move out over the size of the batch update. And we will show that the recurse of this pairwise cover is 1/5. Okay, now let's describe the update algorithm. Like this is, let's just see the easy example first. Like edge insertion is kind of easy to handle. Like because we just need to assign length increase edge to all the new edges. Like just recall that we are allowed to route on the original graph G. So no matter how you add the length increase, no matter how you add new cuts to the original cut, that will not affect the embedding pi. And and it's trivial to see that adding this new cut C new will avoid new edge length demand. So naturally, this new certified ED have the same quality, and it is still a valid certified ED. And the edge deletion is a little bit tricky to handle. Yeah, like for example, like just for simplicity, we assume that N has only one cluster, so we only need to handle one router. And we will show that we can somehow output a slightly worse certified ED with this quality loss. And this is the roadmap of the algorithm. We first somehow get some prune vertices by pruning the dynamic router, and then use cut match to match between like the prune vertices and the rest. Okay, and then the matching part, we can easily reconnect it to the router, like because we have a matching. And the unmatched part, we just decompose it locally. Yeah, let's quickly go through this algorithm. Like the edge failures, like the edge deletions on the router is just like if we delete some red edges in the original graph, like the right-hand side of these figures, we delete the red edges, and this will destroy some embedding path of some router edges. And in this example, we delete the embedding path of green and blue edge, so the deleted router edges is green and blue. Okay, and then we just apply the dynamic router with these edge deletions. Yeah, and the point of these two equations is just to show that the size of the prune vertex is not too large, only blow up by 1/5 fractions. Yeah, and this step, we just kind of match the prune vertices and the remaining part and have a green matching and also some new cut CCM. Yeah, and the green things, like the green matching, we just add it to the router. And because our dynamic router indeed supports these operations. Okay, and here comes the important steps. Like, what do I mean by decompose the unmatched part locally? Here I define local graph to be the vertex induced graph induced by the vertex set P and the union of the matching part of bar P, like the brown area in these figures. Yeah, and I just claimed that we just need to decompose this. Just need to decompose in this small local graph so that after taking the union of the new certified ED and the original certified ED, then we can get our output of our edge deletion algorithm. Okay, here's to summarize what we are doing here. Like we have an input and then have the prune step, which prune some vertices out, and then we connect it through matching, and then decompose the unmatched part locally. And then the output is just the union of two certified ED. Yeah, and sorry about it, I don't have time to talk about the recalls, but basically the recalls of the cut is close to constant because just because when the cut match algorithm will output a small cut, like there will be a 5 factor in the output of the cut size of the cut match, and also the expanded decomposition, the new expanded decomposition will also output a small cut. But there will be a factor 105 when of the recalls of this neighborhood cover, just because the local graph and the size of the pool vertices have size blow up by a factor 1/5. Yeah, and let's skip this correctness. Yeah, and now we finish after we developed the efficient dynamic length constraint expanded decomposition algorithm. We are now ready to construct our dynamic vertex classifiers. So what is a vertex classifier we are looking for? So basically, given a graph G with some terminal T, we want to specify that, okay, it roughly approximate the distance between all pair of terminal vertices that have distance at most edge in the original graph. And this is what I mean, this vertex classifier is only preserving bounded distance. And now our goal is to just first try to construct a static vertex classifier with constant approximation and small size using a static expanded decomposition. Yeah, and here is it's a simple warm up. Like when G is already a length constraint expander, it means assuming it admits H5 certified ED with 0 C. Then it basically means remember that this N is a pairwise cover, like a neighborhood cover, on the graph G minus C. But now because C is 0, so we already have a pairwise cover on the graph G. So the following thing is natural. We just add a stars to simulate the distance inside each cluster, and then take the union of all these stars graph as our final specifier. Yeah, and actually this is easy to see because first the lower bound of the distance in H is easy to see because the diameter of each cluster is kind of small. It's only roughly H. Yeah, but the thing that's not so good is that this classifier only take care of the distance, only take care of the vertex pair with distance around H. So when distance G is smaller than H, the distance of POV in this classifier will become 2H. But what we want is multiplicative approximations. But this is not easy to solve. We just need to consider different landscapes. We assume something stronger. We're assuming that G admits certified ED for different landscapes. Okay, just construct the vertex classifier for all of them and then take the union. And this naturally will take care of all the distance below H. Yeah, and here comes the tricky part, is that when in general the certified ED will possibly have non-zero CI. And how do we deal with these additional cut edges? And our solution is just to add the endpoint of these cut edges into the extended terminal set, and then build a specifier on this extended terminal set. And also add all the cut edges into the specifiers. So why this will work? just because, like, if you consider a shortest path, like from U to V, if there's some cut edges on it, then it's good. Like, you have the cut edges in the specifiers. And for the subpath that between cut matches, between cut edges, like it has difference the same in G minus C and G. So basically, the previous router, the previous vertex classifier can take care of this subpath between cut edges. So now we can obtain a vertex classifier for general graph. Yeah, and okay, let's keep. Yeah, and the size of the graph is kind of small. If we ignore there will be a factor h here because this cut is fractional. It means like the number of cut edges is actually have a factor h blow up compared to the size of this moving cut. Okay, and how to dynamize this with classifiers? Like we just use dynamic certified ED and just keep the invariant that the vertex classifier is always like constructed in this way. And when the dynamic ED change, like when the cut change incrementally, or the neighborhood cover change fully, or the pairwise cover change fully dynamically, it will cause some changes to this vertex classifiers. Yeah, here's some calculation of the recourse of the classifiers. But the most important point is that it depends on the recourse of the pairwise cover, and it also depends on the recourse of the cut in the dynamic certified ED. Yeah, if you recall that, like the recourse of the pairwise cover is 1/5, and this H factor is because the fractional, like because the cut is fractional, then the total recourse of this vertex classifier will become like 1/5 plus H. And actually, this is not good, as Dashboard said before. Yeah, and yeah, we will briefly talk about how to, like the high level idea, how to reduce the recourse of the vertex classifier to make it become close to constant. Yeah, these are the reasons why these factors 1/5 and H are not good. Like just because 1/4 factors 1/5, just because our hierarchy has so many levels, we cannot allow that recourse to blow up by 1/5 factors per level. And the H factor is also not good because finally we will use expanded hierarchy to build emulators. And the emulators will stack for a bunch of levels. And if each levels the emulator have recourse H, this will also make the final recourse become like super linear. That is also bad. And the techniques to solve these two issues, the first thing for 1/5, just is kind of similar to the idea in the normal expanded hierarchy, like we introduced boundary linkness. But to solve these H factors, we will introduce a new concept called landmarks. Yeah, and let's talk about how to use boundary linkness to solve this recourse factor 1/5. And the key observation is that the changes of the vertex classifier, actually we can do a better analysis. It actually only depends on the changes of the pairwise cover restricting on this extended terminal set. So basically, if a vertex is not terminal, then no matter how many times it goes in and go out of cluster, it will not change the vertex classifiers. So basically, we just need to bound the recourse of the pairwise cover, restrict it in the terminal set T bar. How to do this? We assign each vertex in T bar like roughly 1/5 unit of weights, and then recall the dynamic certified ED algorithm. But this time, we only move in or move our terminal vertex from the cluster only when there is a very large units want to move in and move out. And this will roughly reduce the recourse by omega 1/5. So it becomes close to constant. But there's a small technical issue. That is, like if you recall the algorithm, we handling edge deletions. This will bring us new cuts. But now, if you look at the definition of this extended terminal set, it actually includes the terminal of new cuts. So basically, this introduced new extended terminals. Okay, we need to raise the weights of these new terminals. Okay, and it again brings new cuts. But it's actually not hard to solve this problem because we can make this weight on the terminals a little bit smaller, like 1/β5, where beta is some very small polynomial factors. And then like the new cuts will bring like, here we assume h is a constant. The new cut will bring like constant extended terminals, and extended terminals will bring 1/β5 new weights. And then these new weights will bring like 1/β new cut. So this process will finally converge. Okay. And this, like roughly, this is how we deal with the recourse 1/5. And about the recourse factor h, we will introduce some concept like landmarks. Basically, like informally, a landmarks for a graph and a moving cut C is just a vertex set that every cut edges has a closed landmark to its endpoints. Yeah, just ignore this definition. Look at the graph. Like the triangles are the landmarks and the pink are the cut edges. Like we just like the landmarks that we have will be close to like every endpoint of the cut edges, we have a landmark close to it. And an intuitive way to think of this landmark is that this landmark is actually some kind of rounding of this fractional moving cut C. Yeah, and actually we can, when we're maintaining this certified AD, we can also maintain the incremental landmark set, like if like the distance between the landmarks and the endpoint of the cut is not too far, roughly h, and the size of the landmark now becomes roughly like will drop by factors. Will drop by a factor h compared to the number of the endpoints of cut edges. So it is close to roughly linear to the size of the cut. Yeah, and the recourse of the landmark is close to constant. Yeah, and okay, here's some algorithm, like some high-level idea how to initialize these landmarks and how to update this landmark. And yeah, because of time reason, I will skip this. And how to use landmark to reduce the recourse is just, okay, we just substitute like when we construct in the vertex classifier, we just substitute the endpoints of cut edges with our landmarks. And intuitively, this will not like affect the approximation ratio of the classifier quite a lot because the landmarks are close to the endpoints of cut edges. Yeah, and then that finished the dynamic vertex classifiers part. And with these two key ingredients, we can finally build a dynamic LC expander hierarchy. Yeah, and this is how we build it. Like we start with the original graph and then do expanded position. And then we compute British classifier H2 on the original graph with respect to the terminal vertices, which is the landmark of the first expanded decompositions, and then keeps going up. Yeah, and then how to compute the dynamic low step emulator is that, okay, we hide lots of details here, but it basically exploits the pairwise cover of all these expanded decompositions. Yeah, and this is the informal theorem of what we get for our dynamic emulators. So basically, we can maintain a graph that have distance metrics like roughly the same with G, but topped by 8 factors. And the graph size is not too large. And the key thing is that the recurse of this graph is only 1/5. Yeah, but this 1/5 recurse is affordable because we only stack the emulators for like 1/epsilon factors. And if you record how we set this length parameter and congestion parameters, you will find that the final recurse is still bounded by n/epsilon. Yeah, and just make a short conclusion to conclude this talk. Yeah, the key things we want to show is that when solving even purely distance problems in a dynamic setting, controlling the congestions will also be helpful because the update time will depend on the congestions. And the second thing is when analyzing dynamic algorithms, yes, the recurse matters very much, and keep track of the recurse to make it not blow up to become polynomial at last. Yeah, and this is all of my talk. Thank you for listening.